So guys, any questions so far about homework, about class for starting chapter 3? Nothing? Okay. Can you hear me, guys? Just one answer.
Yeah, we can hear you fine.
Okay, great. And you can see the notes.
Yep.
Great. Okay. Yeah, I need at least a feedback. Someone can hear me. Okay, chapter 3. It's about elementary fluid dynamics and the Bernoulli equation. Bernoulli is one of the most important concept in fluid mechanics. Even in the qualifying exam for PhD, we had 4 questions for fluid mechanics. I guess 3, not 4. And one of those were just one was from the Bernoulli. So all the time you will be asked a question about Bernoulli, and most of the time works. Before applying the Newton's second law and talk about the meaning of streamlines and velocity, pressure, static pressure, and those stuff. Let's try to remember a hint from previous chapter. Okay. Just remember from chapter 1.3, I wrote it in the notes, that there are a strong similarity between fluid motion and rigid body motion. Why? Because the law that you are applying here is for the fluid particle, and a fluid particle can be considered as a rigid body. Then all the things that you applied for a rigid body, like a ball, like a box, now it could be applied on a fluid particle. The only thing is that you have to take care of thousands of those particles that move in together. That's the difference. But on each of those, uh, the Newton's law and all the approaches in rigid body motion it works. That's the strong similarity between those. Similarity between fluid motion and rigid body motion. Yes, I uploaded the notes already on the Jubilant, so I will not writing very well here because that one is much clearer than that. And here I'm just copy it and trying to explain what I wrote it here there. So a particle here, a fluid particle could be considered as a solid. Okay. In this chapter, we are doing non-real or imagined consideration or assumption that the fluids are inviscid. So chapter 3, the fluids are inviscid. It means that the mu going to be 0, then there is no shear stresses. Means that the layers of the flow are independent. That is not possible in reality. But that's the assumption that we are doing. And we have to prove the Bernoulli equation. So the main assumption in this chapter is inviscid. That's the main assumption. Okay. So it's also asked that when is an inviscid assumption reasonable? Most of the time it's not, especially when the mu is high for the fluids. But for the gases, yes, it's possible because the gases, the mu in gases are very small. So it depends on how much is the mu, but since we are taking care of the fluid, the forces here, then it depends that how much is this force compared with the other forces are exerting on the fluid particle, right? For example, those can be gravity forces, pressure forces, and maybe electrical or the other type of forces. But the most important one is the gravity and pressure. So when viscous effects are very small, compared to other forces. What are those forces? One is gravity. And the other one is pressure forces. Okay. For an inviscid fluid, the force contribution includes, so one is going to be weight. One force is the weight of that fluid particle. And the second one is the force because of the pressure difference. Right? If that's a fluid particle, and you have a bunch of those close together as a layer of fluid. And here the pressure is P1, pressure is P2. And that's your G, okay? The gravity. Then all of this in each of individual particles, fluid particles, you have the weights as one force. And since P2, we assume that P2 is higher than P1. So we have pressure difference. It has to be P1 higher than P2 because the flow moves from higher pressure to lower pressure. I have to fix that in the notes. I wrote it wrong. But yeah, from higher pressure to lower pressure, the flow moves. So when you have higher pressure behind and lower pressure at the end, then the force would be here in this way, direct to the lower force. And this F, this W is because of weight, and the F is because of pressure difference. What does the other, we are just here, just listing the assumption that we are going to take care of. And we have to consider those before applying Bernoulli's or using those any of the rules here in this chapter. So for one of those is the implicit flow. The other one is that what type of forces we have. And now we are talking about the steadiness and two-dimensionality. So what does the steady mean? That's most of the students have problem with. Steady means flow in a flow, nothing gonna change in time. But this is very important, but at a given location. So it means that if you have a flow in between two layers or a channel, okay, suddenly you freeze the time and read the pressure here and also here. This is P1 and that's P2, okay? And just write it here, these two pressures somewhere, and then let the flow goes, and after time, again, freeze the time and read these two pressures. P1 in the second time should be equal to P1 at time 1, and also P2, but P1 and P2 should, it's not absolutely, this is not required to be equal to each other because the flow is a steady. Steadiness is just means about the time in a given location. And this is like a flow of cars in a highway. So if you're standing close, that's a highway, and you have three lines, okay? You have three lines of the cars. These are different cars, and you are standing here. When you are taking a picture from this side, and you will take care of this part, your image. All the thing that you can see here is the cars are filled because in each line, right? These are the cars here. And all the are moving in this way. If that thing that, okay, this is a busy day and always you can see the cars close together, maybe that's traffic, okay? Or they're standing or they're moving with a small velocity. Then after a time, again, you take a picture and you can see different cars here that passing, but the same picture. All are at the same line and moving with the constant velocity. That's the meaning of steadiness. But sometimes this line, the car is moving faster versus this line. And this is the line that is the slower velocity. Again, after the time, when you take the picture and measure the velocity of the cars, you see the same velocity in this line. But again, make sure that these are different cars, okay? This is one thing. And when we are taking we're talking about the streamlines, the streamlines means that flow lines. So if you are going to write that, draw a streamline for the flow of the cars, these are would be your streamlines. The flow of the cars passing through the lines and at the middle of the lines. But is it true that none of the cars change the line? No, it's not true. These are changing the line, but it doesn't change the streamlines because that's a particle, right? It means that when the particle or fluid particle or this car comes to another line, it again should move on this streamline. So in a fluid, the layers of the particles, if you have particle of fluids here, these are not stick to a streamline. Maybe you have two streamlines, they can come here, that's a fluid. So the layers maybe move, the particle maybe change in the streamlines. But in any streamlines, they are moving with the layers. That's the difference. And you have to understand that when we are talking particle, it doesn't mean that all particles stick to a line and they should have the same pressure because that's steady. They should have the same velocity because that's a steady. These are not, it doesn't mean like that. For example, if you have a particle that is here, then this part, if you track the particle of fluid, it maybe sometimes comes here, right? And you take the pressure here. What does it mean that you have a streamline and you can draw and calculate the pressure and give me the pressure field of the flow? It means that doesn't matter which of these particles coming here, maybe by chance, maybe because of the force balance, maybe it doesn't matter. It maybe this particle starts from here and suddenly show up here, okay? If it's going to pass this point, at this point, the pressure of that would be P2. And the velocity of that would be V2, right? If I freeze the time, and when this particle reach here and take V2 and P2, these are going to be constant. And after a time that this particles died and new particles come, again, if it passed, the new particle passed this point, the V2 and P2 be the same, it means that the flow is steady. That's the meaning of steadiness, and it's not doesn't mean that all particles have the same, and it doesn't mean that the particles should be strict to a streamline. These are the flow of the moving those particles, but the particles again, like in molecules, they are free to move between layers, and that's why these two are a little confusing because we are talking flow and function of the flow and the streamline versus the path line. The path line, anytime that you see that, what is the path line? The path line is that when we track one of the cars in highway, so the cars maybe come in the highway and then switch between the lines. These are the track. So maybe that's an arbitrary plot. But when we're not talking about the flow, all those have to be, when they are a highway, they will move on the lines. And the lines are smooth and is based on the shape of the highway. These two, you have to understand that these two are different. And the equation for those is going to be different. Why I'm talking about that? Because here we are going to talk about the streamline. So after I'm just writing here, the two-dimensional thing means that the flow is in XZ plane. That's only assumption for now. Absolutely, the flow could be in XYZ, but here, because we are going to take care of the, just consider the inviscid flow, then the pressure would be only change because of the static pressure only change because of the Z. So we only consider X and Z, but doesn't matter why right now. Okay, for a steady flow, particles will follow the same path, and the same vector is, and the velocity vector is always tangent to the path. When we can streamline coordinates to identify how the fluid moves. here you can see one of the fluid particles. If that's a fluid particle, then the velocity of that is always tangent in tangential direction. Okay? You have one tangential direction and you have a normal direction. Normal direction means that is normal to the path or normal to the tangential direction. And also for this particle, you have S, which is the distance and the line that the particle passes on a streamline. So S shows the distance, and is normal direction. Okay. What about R? R is the local radius of this curvature. If that's the curvature, and you can say that you have a circle here, then it has a center and it has a radius. That radius is a local radius of curvature. Okay. So we are starting with a particle to find what is the velocity of the flow. Again, the velocity of particle is different with the velocity of the flow at this point. At this point, yeah, these two have the same, but the flow velocity is not always similar to the flow velocity and acceleration of a particle, because this particle may sometimes be here or somewhere else. So first, particle motion. We have to start with particle motion. Is a function of S. So S function of the T. You see, this is a steady flow. We wrote it here that the flow is a steady state condition, but still we have T. How is it possible? Because the flow is steady when you take a different picture at a time from this flow. Always the streamlines are the same, but it mentioned that the flow, the paths that this particle moves are the function of time. Why? Because the flow, when the particle starts from this point, at time it moves, and that means that the motion of the particle is a function of time. So S is only for the particle, and the particle motion is like S of t. Particle velocity would be V of t, which is ds dt. Derivative of the motion of particle motion versus time. What you got the acceleration? Is dv over dt, right? But v is not directly function of t. It's function of s and then function of t. So for now, we are writing that as as times direction of s. That's the tangential direction, plus an times n, which is the normal direction. So two terms are here, 1 and 2. Okay, you have to write those and find the equation for that. So for the first one, which is along a streamline, along a streamline means s, which is tangential direction. What is the derivative term? Is as is equal to dv over dt, but we know that the v is not a direct function of t. So the chain of the derivative needed run the V over S and ds over dt. But from this point, we know that ds over dt is V, right? So can write that AS is V times velocity times run V over derivative of V versus S. What about the second term? The second term is the centrifugal for acceleration, right? Because of the curvature that you have a centrifugal acceleration. Then this is centrifugal acceleration, and it shows by AN. How we can calculate it? AN is V to the power of 2 over R, right? You have to know that from dynamic course, maybe. That's the velocity to the power of 2 over R. Now we can write that what is A as a function, the vector of A is V S AS, I'm sorry, AS is S, direction of S. Of S plus R of R, which is the radius, times N. Okay, that's your equation for acceleration. So what we have till now, we have velocity, which is the ds over dt, if we have the particle motion as a function of time, the location of the objects when passing through the streamline. And we have the equation for acceleration. So the derivation shows the relation between the particle force due to pressure and gravity. So you see that in the equation that we have, and sorry, here you find two terms for velocity, the acceleration terms, right? One of those are along a streamline and the other one is a normal to the streamline. Here, based on the Bernoulli's equation, the total energy that the particle have is summation of the pressure, which is a static pressure. Why? Because those are the different forces. So you know that sigma F is equal to ma, right? What are the forces? One is the pressure force. I'm just writing P. And the other one is because of the gravity force, right? mg is equal to the mass of the flow times A, right? So what we have here, gamma z is responsible for the flow weight. The other one is velocity squared, which is exactly, this is v squared over r. That's one term for the acceleration that we found. And the other one is v times dv over ds, right? That's also combined in this term. Okay, you don't need to be worried about how we found this. But right now, the only thing that you need to understand which of these terms is related to come from where. The pressure is because of the pressure force. Rho times here because you have rho times acceleration, and rho is a responsible for the mass, right? mass times acceleration, and two terms of acceleration. One is the stem, which is for the tangential direction or along the streamline. And because of tangent to the streamline. And this one is cross the streamline because it's normal direction or normal to the streamlines. Okay. So it is show that when you have a steady state condition and you know that nothing gonna change in time, but it will change in based on location. So along a streamline like this is one streamline, right? Along the streamline, this summation of all the forces, pressure force, the acceleration and mass, which is the force because of the acceleration and change of velocity. And yes, we have change of velocity because that's the streamlines, but always the velocity is tangent to the direction. So it could be changed, or at least maybe it's not changing the amount of velocity, but because of the change of direction, the change of direction, if you find the velocity here, this is tangent to the direction. So maybe direction of the velocity change. So here, the direction that you have here is changed different with that direction. So you have velocity change. Velocity change means that you have acceleration. The summation of all this going to be constant over along and across of a streamline. When you're talking about along a streamline, that's the Bernoulli equation. And Bernoulli only valid along the streamline. Okay. Physical understanding of that means it's like rigid body motion. It means that the kinetic energy in total, because we don't have anything that energy is not dissipate, is not generate. So the total energy of the particle, which is like a rigid body motion, rigid body, is always constant. Okay, only the type of that energy changes, right? Sometimes it's stored because of the weight. Sometimes it's going to change to the pressure or higher pressure, and sometimes change to the kinetic energy, right? So the total energy that shows up here are constant, but maybe different phase. It shows like a in gamma z or change to kinetic energy because of velocity or sometimes because of the pressure. So it depends that when the flow passes and the fluid particle pass, it's possible that have higher pressure, but when you have a higher pressure and you are moving in the same z, then absolutely the velocity comes down. It's like having a ball that you're standing on top of a roof and you keep a ball here. Then you leave it to come down. Here, the total energy is the velocity is 0, is equal to rho gh, right? If you remember from the physics or holiday, I guess. There's only energy that it has. But when it comes down and it's here, it's still coming down, it has a velocity, right? Then the total energy is the same as top, but it changed to hs prime nu h plus the kinetic energy. And when it reached to the end, the whole velocity, energy change to velocity. So the total energy is only V squared. And because h equal to 0, you don't have energy because of stored energy because of the height. That's the difference. So the same thing is here, but Bernoulli bring it into the fluid motion and give us an equation. So here is very important when you are going to apply Bernoulli that you have to always check the assumptions. And if the assumptions are matched, then you can apply. So let's summarize the assumptions. One, flow should be steady. Second, flow is inviscid. It has to be inviscid flow, means mu equal to 0. When this is applicable or reasonable assumption, then you can apply Bernoulli. 3, flow is incompressible. We didn't talk about that till now. So when this come from? It comes from this meaning that the flow, the parameter of the flow, shouldn't change in time, okay? When you have a compressibility situation, then the rho is going to be changed, maybe because of the compressibility. So the more compressed the flow is, then the density is going to change. So one of the assumptions that is rho should be constant, then you can apply Bernoulli. And finally, Bernoulli, or this equation of the Bernoulli, only valid what's happening here? Someone shooting on us. Along a streamline. Okay, these are 4 main assumptions. That's on a streamline. You have 4 points here. 1, 2, 3, 4. For all these 4s, all 4 points, if you find the P1 plus 1 over rho V1 squared, the velocity that you have at this point, plus rho G, which is gamma, in Z1, based on the reference number, like C, this is for reference Z, okay? And that would be your Z1. And in point 2, you have P2, different velocity, maybe magnitude and also direction, plus rho GC2, okay? If that's equal to constant 1, this should be also equal to constant. And other thing is that when you have 2 lines here, this is not absolutely, these 2 are not absolutely, or it's not required to be equal to each other. Just in specific conditions, these 2 could be equal to each other, but it shouldn't be always equal to each other. So you have C1 here and C2 here, but all the points in the streamlines have the same amount of total energy or the summation, okay? Oh, let's talk about the pressure here. The flow passes through a channel, and we put a piezometer here. That's a piezometer. But before I start this part, any question till now? None? Okay. You remember from the previous chapter that we can get the static pressure, right? This pressure here is static pressure. So can we apply that here if we want to know what is the pressure at point 1? At point 1, what is the pressure? Any answer for that? So this is the question. Can we write the P at point 1 is equal to, you have height of the fluid. So weight of the fluid on top, of water times H. Is it correct? No, it is not. Why? Because at point 1, the flow is not at rest. That's the problem. So when the flow is not at rest, the pressure is the pressure that only is not dependent to the flow, the fluid that is on top of it, right? If you suddenly stop the flow here, then you can see that stopping the flow means using a piezometer. You can see that the flow line moves upward because that's the true pressure study. So here at point 2, the velocity is 0, right? When the velocity is 0, it means that we generate a stagnation point here. Stagnation means that you suddenly make the flow velocity equal to 0. So you have a stagnation point here. And in a stagnation point, the velocity is 0. When the velocity is 0, then you can say that here the flow is at rest, right? Then if you can see that the velocity, these 2 points have the same pressure. And if you find the weight of this flow using the equations in the previous chapter, then pressure at point 2 is absolutely gamma water times capital H, right? The capital H times gamma water, that's true because here the flow is at rest. At rest means that it's not moving. But here at point 1, it's not true. I have another question. At point 3, can I use that equation? At point 3, what is the pressure? Yes, you can. Why? Because close to the wall, these points are not moving. Let's say that the point 3, the flow has 0 velocity. If it has 0 velocity, then this is going to give you the pressure. But the point is that our question is that how we can find the pressure at 1. Using pressure 3, can we use to find the pressure at 1? No. Why? Because the only way that you can find the pressure at point 1 is applying Bernoulli, right? You're going to apply Bernoulli to find pressure at point 1. But Bernoulli, has 4 assumptions. Assumption 1, flow is steady. So we can assume that the flow is steady. Inviscid, okay, somehow we can say that, okay, it's inviscid. But the fourth one, valid only on streamlines. Point 1 and point 3 are not in the same streamlines. The streamlines are shown here, and it's going to stay the same till here. Point 1 and 2 are the same streamline, but point 1 and 3 are not. So you cannot apply these two and use these two for applying Bernoulli, okay? So if you apply the Bernoulli, here, the total pressure is rho times Q. So the total pressure at point 1 should be equal at point 2. Is it correct? Because of Bernoulli mentioned that. The total pressure at point 1 is the static pressure plus pressure because of velocity and the gamma z. Okay, all of these has a name. This one is a static pressure. This is the dynamic pressure. And that's the hydrostatic pressure. Summation of these three gives you the total pressure and is a constant along the streamline. So PT1 and PT2 are equal. If you are going to calculate the pressure point, the static pressure at point 1, right? Plus, you have to write that, plus 1 over 2 rho V1 squared plus gamma Z1, okay? This should be equal to in all points at the same line should be equal to each other. So we write that the other side at point 2, P2 plus, this is static pressure again, plus 1 over 2 rho V2 squared plus gamma Z. Here we have the same Z. Doesn't matter where is your reference, but let's say it's here, but these two have the same Z. So these two are going to be canceled out. And also the velocity at point 2 are 0. So it mentioned it can be concluded that pressure at point 1 is pressure at point 2 minus 1 over rho V1 squared. Using Bernoulli, most of the time you can clearly calculate or measure the velocity at point 1. And also if you put the piezometer here, you make the velocity here 0, and you can measure the height and find the pressure, static pressure at point 2, right? When you have the pressure because of the height, or reading the height here, you have pressure at point 2, static pressure, and you know the velocity here is 0, and you can measure the velocity at this point. Then using Bernoulli, you can find the pressure at this point. That's the importance of knowing about Bernoulli and applying that over a streamline, along a streamline. So before solving a bunch of the questions, the only thing that you need for Bernoulli is just question examples. You have to do it, you have to write it, and trying to apply the Bernoulli and try to understand how to apply it. That if you could do that, then this is very interesting chapter for you. So let's summarize the important definitions here. First is PT, is the total pressure, right? When we only write P, means that static pressure. And rho V squared over 2 is dynamic pressure that we talk about that. So if you just write the Bernoulli equation, that this is going to be a constant number, and multiply each side by 1 over gamma, which is rho G, then the P is going to be P over gamma. Rho V squared over 2 is going to be, if you multiply by 1 over rho G, the rho and rho going to cancel out, and V2 V squared over 2G is the final term. And gamma is going to cancel out with the other gamma, you will have Z, okay? Doesn't matter what you have here because rho G is a constant number, G is constant, and rho is a constant, and this is a constant. You can only consider the new constant here, okay? But all of these three have a specific name. These are the total pressure, and P over gamma is going to be your pressure head. V squared over 2g is your velocity head, and z over z is your elevation head. Okay. The other thing that we talk about, and we are going to summarize here, is the flow and piezometer. Okay. When you have a flow and you want to find the pressure, static pressure in any point, you will put the piezometer here, and the flow, because it's stopped here, and the velocity and is open, and this long tube is coming up and up and up some way, and in some point it's going to stop, and it's going to be at rest. So velocity at all these points are zero. Then you can see that the velocity at this point is zero. Then pressure that you have here is a static pressure. Okay, this point is a stagnation point. Stagnation point means pressure at the stagnation point is stagnation pressure, and stagnation pressure is a conversion of kinetic energy into pressure rise as the fluid is brought to rest. So suddenly brings the flow to the rest and read the pressure, and is the pressure the static pressure. We told before about the total pressure along a streamline. So as I told you before, each streamline has a specific constant, and all the points are the streamlines have the same total pressure. So P2, PT, or total pressure on all these points are similar. For C1, C2, and C3, these are the constant number, and it's not required to be equal to each other. But sometimes, that we will talk about later, if condition, specific conditions be valid, then you can say that all these points, that C1, C2, C3, all are equal each other. It is possible, but you don't need to be worried about that. That's the only thing. I don't think that we can talk about that this semester, but that's when your flow is not, it doesn't have any circulation. It's non-circular, then you can say that the Bernoulli and the constant number is all similar. Any question till now? Okay, let's solve an example using by applying Bernoulli. Okay, a manometer is fastened to a pipe to measure the velocity of SAE oil as it flows at steady state. Steady, the first assumption. The manometer is designed to read the static and stagnation pressure of flow and uses water as the gauge fluid. Here is the water and it's the flow of the oil. Determine the upstream velocity. What is S? What is S velocity? What we know here from, let's check the assumptions. First, the flow is steady, perfect. The second is that this one has, it could, because it's a heavy oil, and it's incompressible. Okay, so that's incompressible flow, and this is our second assumption. What about the third assumption? What was the third assumption? Is inviscid flow. Yep, we can do it. So let's assume that this is inviscid, okay? Doesn't mention, it didn't mention the question that is implicit, but we can assume that. That's our third assumption. Along a streamline, we should decide that where is the streamline. And yes, absolutely. If you are going to find the velocity here, you have to apply Bernoulli along the streamline. Okay, never try to apply Bernoulli in 2 points that are not in streamline. Let's put two numbers here. 1 and 2. Okay. This is our good point. Let's say it's 0.1. And this is our 0.2. Okay. And let's apply Bernoulli. If you apply Bernoulli equation, it means that the total pressure at 0.1, it should be equal to total pressure at 0.2, right? Total pressure at 0.1 is what? Is P1, which is the static pressure, plus 1 over 2 rho V1 squared, plus gamma Z1. And what is the total pressure at 0.2? The same, P2 plus 1 over rho 2 rho V2 squared plus gamma Z2. And from Bernoulli, these two should be constant. And since you are on a streamline and the one streamline, then these two also equal to each other. Okay. So P1 plus rho V squared over 2 V1 plus gamma Z1 is equal to P2 plus rho V2 squared over 2 plus gamma Z2. Okay. Or if that's our reference point Z, are Z1 and Z2 equal to each other? Yes. So let's cancel out Z1 and Z2. And the flow here is at rest, right? So at 0.2, the flow is at rest. That's why we use piezometer. This is also 0. Then also we know that V1 is the V that we are looking for, right? And I will bring the P2, keep P2 on one side, minus P1 is equal to rho over 2V squared. That is the V that we are looking for. And then V is equal to 2O 2P2 minus P1 over rho squared. That's the equation. Okay. We know what is the rho. Yes, we know it from the SAE 30. We can find it somewhere. But do we know what is P2 minus P1? That's the question. What is P2 versus P1? Okay. From here to here, if you put the 0.1 in this side, from here to here, the Z's are similar. The V is similar. The velocity doesn't change from point here to point here. Okay. And also the pressure are the same. So 0.1 if you use point 1 here, has the same velocity as this point. So that's why I put those points as a 1. From here to here, you have to find the pressure difference, a static pressure difference. You don't know what is that, but the water and the piezometer are going to show you what is that, okay? To find the pressure, static pressure difference, or P2 minus P1, you can find it from here. If I just put the H to name here, okay? And from here to here as H1, okay? And then apply our methods from the previous chapter and move from point 1 to point 2 and try to escape, right? Start from point 1. If you start from point 1, then P1 is your start point. Then you have to move from point 1 to this point, right? Why? Because the fluid is going to change. So is or H star, right? From here to here is or H star. So minus, you're going down, so positive. What is the gamma? Is gamma of the oil. What is the descent? The height that change is H star. Then from point here, which is or point 3, you are moving to point 4, right? From point 3 to point 4, you have H1 minus H star, right? Okay, so plus, again, gamma is gamma water, and you have H1 minus H star. Then moving to this side, and this point are the same. Is the same height from here to here is the same height. Okay, so from here you can move up to point 2. Okay, because there's nothing going to change from here to here. So from this point, which is or point 5 to point 2, you're moving forward, negative. The gamma is gamma oil, and distance is H2. Okay, reached point 2 minus P2 equal to 0. Okay, so gamma water H1, gamma oil H star. Is it true to write that H2 is H star plus 0.02 meter? That's height. It's 20 millimeter. Yes. So if I replace that with gamma times minus P2 equal to 0, and I have gamma water times H1 minus gamma water H star, right? And also H star minus H1, H star, which is from here to here, minus H1 again is equal to 0.02 meter. So this is also 0.2 meter, right? So gamma water 0.02. And P1 again is here, plus gamma water, gamma oil times H star plus here minus P2 equal to 0. So then this is going to be cancelled out with that. And as a result, P1 minus P2, or if I bring it the other side, P2 minus P1 is equal to gamma water, or 0.02 times gamma water minus gamma water. If this is 1 and this is 2, then using 0.1 and 2, you can replace or plug in 2 in 1. V is equal to 2 times 0.2 times gamma water minus gamma oil over rho. This rho is raw oil, right? This is raw oil. And I'll write the final answer. You can calculate by yourself, but just to have final answer, the V is 0.193 meter per second. This is a question. Not hard that much, but it was good. This is a question that is combination between the equations of the whole your understanding from chapter 2, which is static pressure, because you are applying the piezometer, and the meaning of static pressure difference because of the fluid weights, and also at the same time you are applying the Bernoulli's because the fluid is moving. So it's moving the fluid on top, and also here you have fluid at rest. That's the combination between these two, and that's why it's a little better than a simple question. So it's medium type question. I will put this also add to the notes. I forgot to add it. I will add it to the notes for this chapter. This is part 1 of the chapter, and next week we will talk about the second part and maybe solving more questions if I get time to do that. Or I will upload a bunch of more questions and top questions in Jubilant. You can follow it. Next week, we have to start dimensional analysis, chapter 7, because we are a little behind. And yeah, that's all. Any question? Just homework 2 also released. The deadline is next week. I extended the deadline for homework 1 because bunch of your students have problem with question 4. I don't know. I do my best to almost give the answer, but still students have problem. I guess the problem was sometimes MATLAB and sometimes fitting problem. But hope that everyone submitted the homework. Any question till now? Jake, you. Oh. Anthony. Almost Ali. Okay. Have a good day, guys. That's enough for today.
Have a nice weekend.
You too, Jake. You always are here, right?
Yeah, I should be.